Okay,
Great.
so let me go back up. Okay. So you guys can see the slides? Okay, so hi, my name is Rosario Gennaro. I'm a professor at the City College of New York. Today I'm going to talk about a work that we finished last spring with this large group of collaborators. Pranay Churi and Matteo Campanelli were researchers at Off-Chain Labs. And then Paul Cesaretti, Asan Kaiman, Tuju Samir, our PhD students here at CUNY, and Tushar Joyce is another faculty here. Tushar and I are part of the Cryptolet project. So the goal of this paper is to talk about how to do some sort of cryptographic verification of the behavior of large AI models and what we called verifiable AI. So let me, so just one second, I have a window that's sort of buzzing. Okay, close that. So what is verifiable AI? So verifiable AI refers to artificial intelligence systems that have been built with some sort of ability to verify their behavior. So in particular, we are thinking about the ability to explain why they behave in a certain way, or the ability to audit and account for their behavior. So why is it important? Because we have AI pretty much into everything these days, and in particular, there are applications that are very, very sensitive, like medical diagnosis, autonomous vehicles, and financial services, where you may assume that the model that you're running has been designed with the best interest in mind, but if you're running this model on an untrusted platform, or if you're just running it somewhere where you don't know what is actually being run, then you may not be able to trust the results that you're getting. So there are two parts, as everybody knows, in AI. The one is the training of models over large data, and then once the model has been trained, the model is deployed and is used to run inferences. So you present a prompt and you get a response. And that is the focus of our work. We're going to focus that given a particular model that has been already trained and that we believe is actually a good model, then the moment we present a prompt to this model, we want to make sure that the answer we get is the answer of the model that we believe should have been run. So why are we focusing on proof of inference? Is because all these large deep neural networks have been deployed on platforms such as like a cloud-based services, or by the companies that actually run them. You don't run the model on your machine. You send the prompt over the internet to somewhere where this model should be run, and then get an answer. And how do you know that that's actually the model that you were promised that was going to be run? So here's an example. You have a AI model that gives you financial recommendations on stock trading, and this model has been tested and maybe approved even by regulators such as the New York Stock Exchange. And then you start querying this model, but this model is being run on an untrusted platform, and you don't know if you're getting the answer of the actual model. So okay, and that's exactly what I said. The model might have been replaced to gain advantage, or just even by some bug in the code. Or another reason you may be interested in to do this is that you have a model that was trained. One of the certification that this that you sort of train the model on data that was legal to train it on, but you also then trained another model on additional data that you were not supposed to, like copyrighted data or private data or something like that, and then sort of sneak in this different model because it has better properties than the one that was also only limited to the authorized data. So those are things that we want to try to avoid. There are other motivations that were presented to us by reviewers of this work, which is one of them, which we weren't aware, is fair washing. Fair washing basically is a way to make a model look good during audits, but then sort of then display behavior that, for example, is the model is not fair, the model is not safe, but all of this explanations are during the auditing, the model is actually able to behave properly, and then somehow in the wild, this actually bad behavior sort of surfaces. So for those of us who are cryptographers, we sort of know, we have been known for now almost 40 years that, at least in theory, it is possible for a party who runs a computation to prove to another party that the computation was done correctly. So these are cryptographic proofs that have been around since the mid-'80s with the introduction of zero-knowledge proofs. So you have a computation C, you have an input X, and the prover runs the computation and generates also a proof. Look, this is actually the result of running this algorithm C on this input X. And the verifier will run the proof, check the proof, and will accept or reject depending if the proof validates or not. And here, in this example that I have on the screen right now, the most important thing is that because the computation is deterministic and there is just an input, the verifier could actually rerun the computation itself. But in this case, the usefulness of this kind of cryptographic proofs is when the verifier doesn't have the time to run the computation. So in this case, we present proofs that are much faster to verify than actually the recomputation itself. Another reason where cryptographic proofs are very useful is in the case of zero knowledge. In this case, there are two inputs to the computation. One is public, but the other one is private. Things, for example, I have enough money to qualify for this loan, right? So X is the amount of the loan, is public, and W is my bank balance. I want to just prove to you that I have enough money to qualify for this loan, but I don't want to tell you how much money I have. So in this case, the verifier will not be able to recompute the computation because it's crucially missing one of the inputs. But there is a way to convince the verifier that the computation is actually correct. In this case, I do qualify for this loan, and with a proof that reveals no information about the second input that we call usually the witness. So these were very beautiful results that came out. The zero knowledge actually came out first in the 80s, and then later in the early 90s, we came up with this notion of proofs that are faster to verify than the actual computation. So given that we have all this beautiful literature on cryptographic proofs for any computation, in fact, that's actually one of the classical results. You can take any polynomial time computation and encode it in a way where you can build these proofs. What is there to do? So, well, it turns out that cryptographic proofs have very, very large overhead because the way you build these cryptographic proofs is by encoding the computation in elementary steps. And for every elementary steps, you have to do some expensive cryptographic operation. One of the best results for large language models, this paper that appeared about a year and a half ago at CCS called ZKLLM, maybe 2 years ago, requires about 15 minutes to prove a large model with 13 billion parameters. And even the authors themselves sort of acknowledge that without any revolutionary idea, it would be very difficult to get any better than what they did, because just the cryptographic overhead of the cryptographic proofs it was just too large. There's actually it just came out. I didn't have time to update the slides, but there's a paper that just came out on ePrint by this company called Lagrange, where they get numbers that are slightly better than this ones, but we're still in the order of minutes for proving a correct inference. And this is a big problem when you're talking about verifiable inference, because inference is the kind of stuff that you do all the time with AI models, right? You send prompts all the time, and you want answers all the time, and the process of producing these answers should be very fast. And if you want, so basically verifiability should come at almost zero overhead. This is not the case with training. In fact, with training, which is a more expensive process that happens not as often, having a 50-minute or a 30-minute, or even a day time to generate proofs may even be acceptable. But for inference, this is completely not acceptable. To have order of minutes into even seconds to produce proofs. So the question that we asked ourselves when we started working on this was, how can we produce an efficiently verifiable proof of inference without slowing down the actual production of the inferences? So we came up with a solution. So I'm going to be very upfront right now that when we submitted the solution for publication, we thought the solution was much better than it actually is. In the process of presenting it and talking to people from AI, some issues with the which I'll explain in the rest of the talk. So it's not a cryptographic proof in the classical sense, where it's basically impossible to cheat, but we have a slightly weaker bound on the probability of success for the adversary. I'll get into that in a minute. But what is our solution? Our solution was to zoom in on the statistical properties of neural networks that would allow us to only check random parts of the execution. Remember what I told you, the big overhead of cryptographic proofs is that every elementary step of the computation has to be checked. And to check, you need to introduce this expensive cryptographic overhead for every simple execution step of your code. In the case of LLM, we had this sort of intuition that they're very large statistical computations. And when you if you present an output that is very different than the output that you should have presented, you may catch this problem by looking only at certain random parts of the computation. So what we did was, the prover runs the network and just commits to the execution trace, meaning all the intermediate values of the computation, and think of committing as putting all this into an envelope. And then as a verifier, I'm going to ask the prover to open only a random selection of these intermediate values, and I'm going to check only these intermediate values for correctness, and hopefully I will catch the prover in its lies with a sufficiently high probability. turns out that this this approach resulted in a proof that can be generated order of magnitude faster than previous approaches. We went to milliseconds instead of minutes, and I'll get into that also in the rest of the talk. So here's what are we giving up. Seems to be too good to be true, right? So what we're giving up are three main things. The first one is zero knowledge. Our proof is not zero knowledge. In this case, the zero knowledge would be maybe some proprietary parameters of the network, right? So say that I train this network. I'm very protective of this network, and I want to prove to you that I'm using the correct network, but I don't want to reveal to you how the network works. So then in this case, you need a zero knowledge. Our proof does not guarantee zero knowledge, and in fact, actually reveals quite a bit about the network itself. The other thing that we're giving up is exact correctness. And what do I mean by that? Because we're using the statistical properties, you'll see later, I'm not going to guarantee that the result that I'm presenting to you is the exact result of running the model on the input, on the prompt, but it's rather close enough that I haven't really presented you with something really, really far from the correct input, according to some certain metric. And the third property, which I already hinted a little bit, and that was the one that we were aware of the first two from the very beginning. The third one was the one that came up as the paper went through various iterations of reviewing, was that we are also giving up negligible soundness. So the prover will be caught, but will be caught with a probability that is not as small as you want it to be, but it's usually the which depending on the application, and I'll get into that, may not be enough soundness probability. So those are the what are we giving up? So we couldn't get to such much better speed without sort of lowering our expectations on something else. So what is the key intuition? The key intuition is that if two models behave very differently as functions, then their internal behavior should also be very different. And this internal behavior, this internal representation should be so different that by testing a small number of neurons, we should be able to detect that I'm using M1 instead of using M2. That's basically the idea. This turns out, so basically, I tasked my graduate students to go and look at the AI literature to see if this is something that people who do work in AI models actually have experienced. And turned out that there's this notion of similarity that people it comes out from the area of AI, not surprisingly, that looks at explainable AI, try to understand, to explain how knowledge is generated inside neural networks. And so there's a notion of functional similarity that measure how similar are networks as functions by comparing their outputs behavior. And then there's a notion of representational similarity that instead looks at the difference between the internal intermediate values that the two models compute. And there was a very revealing sentence in one of the surveys that we found that says that if two models are not similar as functions, then there must also be not similar in their internal representations, which was exactly what we were looking for. So this was the first sort of step that told us that we were on the right path. So let me tell you now a little more specific. What do I mean by representation? What do I mean by trace? All these words that I've been using without formally defining. So I hope many of you already know what a neural network is, but a neural network is basically a large directed acyclic graph, usually built in layers. And these layers are connected by edges. And in every single neuron, you can think of it as what we call a perceptron, which takes as input the values of the neurons of a subset of the neurons in the previous layer. These inputs are you take a linear combination of this input with some weights that are associated with the edges. The weights are the parameters of the model, while the x's are generated from the input, because the input is the first layer of the model. So you do this linear combination. This is this purple sum node. And then the result of this linear combination is fed into a non-linear activation function, which then gives you the output. So you start by putting the input in the first layer, and then you propagate through this basic, very simple property function, and then the output will tell you will be the result of the function of the last layer, will be the result of the function of the model. And for example, in this picture, we have a model that recognizes if a picture is a cat or a dog. So you take the picture, you discretize it into values that go into the first layer, and then it goes through, and then at the end is going to tell you a single bit, which is either a dog or a cat. And you train these models, which means you determine what the appropriate weights are. And once you have a good trained model, you'll be able to, given a prompt, determine if it's a dog or a cat. So now let me tell you what I meant by a trace. A trace for us is all the values in all the neurons of this model. So that is what we call a trace. And the trace is computed as layer by layer in this manner that I just described. So, okay, so let me tell you. So what is that we're trying to do? We want to prevent a malicious prover, the adversary, to claim that the output was computed that they present is different than the output of running the model on the query. We assume that the adversary knows the correct model. We also assume that the adversary is polynomial time. So, and now, to sort of reiterate what I already said before, we are going to assume that if I'm going to run, let's assume for a moment that the adversary runs a different model, right? So instead of running the correct model, the adversary runs a different model on the prompt. And if the two models are very similar as functions, then I don't care. This is where the exact correctness, I gave up exact correctness. So he's running a model that pretty much behaves as the correct model. I'm good with that. But if the model is very different in terms of output, then, as we said before, they must be very different also in this the vector of traces. The trace of the model 1 and the trace of the model 2, and now you guys know what a trace is, must be very, very different from each other. And now we need a test to detect which one of the two traces, or if the trace that was not the correct one was used. So let me tell you now how the proof works. So first of all, and you see this box up here that says CM. So there is a model that has been trained and has been now put into an envelope. And now the prover is going to convince the verifier that the output is of the model that was put into that envelope. So we're working in a model in which theoretical model, in a framework, in which our AI model was trained and was sort of certified by some entity that this is the correct model that needs to be run. So in this case, we're going to assume that the prover is going to send back the result and is going to allow the verifier to look at certain parts of the trace. And then the verifier runs this efficient test on the trace and will be able to detect if the actual model in this envelope was run. And this will be done with a very small number of queries. And the test will fail if the adversary is running a very different model than the correct one. So we're assuming that the adversary has a very, that the verifier, so I already said that the adversary is running a different model, but also the verifier has complete access to the trace. Well, I'll tell you later how. So say that the entire trace is put in front of the verifier, which of course is too much for the verifier to handle, but the verifier will only look at very few spots. And then I'll show you later how to not give the entire trace to the verifier. But let's assume for a moment that the verifier can see anything in the internal execution of the model. So our first guess was pick a random node and pick all the parents, I mean the nodes on the previous layer that feed into that node. And now look if the equation of the perceptron actually works. So you look at the previous parents, you look at the value at the claim value, and you look at all the weights. This is where our protocol is not zero knowledge. The verifier needs to see the weights of this particular node. And if the equation is satisfied, then you accept. But if the equation is not satisfied, then this means that the prover is running a different model. Now the question was, how many nodes are bad, so that will tell us the probability that we're going to catch a bad prover. So we ran some experiments, and turns out that this is not a very good test, because when you look how the models start deviating from each other. So think about the model that recognized dogs versus the model. We ran it. One of the examples that we used was a model that differentiates between dogs and cats, and a model that differentiates between dogs and squirrels. The two models actually at the beginning behave very similarly, and that's because they're learning very similar low-level features like the boundaries of the picture, or it's also only later into the depth of the network that the two models start distinguishing. And if you just pick a random node, and you're going to pick a random node at the beginning, then this is not going to tell you anything. The test is not going to detect, because at the beginning the two models are actually not that different. So this sort of told us that we had to actually look at something that go through the entire depth of the model, and we developed this other test, which we call the random path test, which says select a input node and a random, and then basically select a node and then go through a random path from the beginning to the end. And now verify consistency for all the nodes in the path. So the query that the verifier now does is, you pick the random path, and then for every node in the path, you pick the nodes that feed into that node. And so now you can do the test, the single node test on every node into the path. Now, sorry, I thought I had another slide here. Okay, turned out that in our experiments, maybe that slide is later, this test performed a lot better than the random node test. So remember that in this case, the verifier is assumed to have access to any, if he says, I want to see this internal node, and I want to see this internal node, and I want to see this internal node, he has access to it. So how do we provide access to all these values to the verifier? Here is where we use the notion of cryptographic commitments. So if you see, there is, instead of sending the entire trace to the verifier, we send a commitment to the trace. And the kind of commitment that we have to use is called a vector commitment. A vector commitment allows a party to commit to a large vector. And again, think of a commitment as I'm putting this large vector into an envelope, and the envelope can be very, very small. It could be much smaller than the size of your vector. What is interesting about a vector commitment is that it allows me then to open single values of the vector. In a typical commitment in cryptography, where I commit to a value, I have to reveal then the entire value. But here, a vector commitment will allow me to, for example, just open VI and prove to you that the VI is really what I have put in the envelope at the very beginning. And both the commitment and the opening proof of each individual value are small. Small meaning constant or sublinear in the size of the vector. So now, and the typical implementation of vector commitments is Merkle-trees. For those of you, many of you should be familiar, but in a Merkle-tree, you put the vector as leaves of a binary tree, and then you hash pairwise each leaves until you get half and half and half until you get to the root. So now, no matter how big your vector is, the commitment is a constant value. And then to open a particular leaf, you open the path that goes from the root to that leaf and the siblings that hang off the path, because that allows you to recompute everything up to the root. And if that works out, then you know that the opening was correct. And this is based on the fact that you're using collision-resistant hash function to build this tree. So we use Merkle-trees in our code. It's not the only possible vector commitment you can use, but Merkle-trees are the most efficient ones. So remember that the verifier needs access to the weights and access to the activations in order to run that single node test on every node on the path. So for the weights at the end of the training phase, there will be a vector commitment to the weights of the correct model. Think of this as our ground truth, right? This is what I have to prove to you that I'm using a particular model. This is what grounds the model that I'm using. And then the random access to the activations is given by the prover. The prover commits to the trace and then opens the values that the verifier requests. So now this gives us the full protocol. So there is at the end of the training, a vector commitment to the weights is generated by a trusted party, or maybe even by the verifier himself, if they were the ones who trained the model. And then the model is deployed on an untrusted platform, say the prover. A query is presented to the prover. The prover presents the app with a full commitment to the entire trace. The verifier asks for a bunch of queries on the trace, the path test, gets the answer, and does the verification. And accept if the path test works, otherwise it rejects. So here is an interesting point. Now, the commitment to the trace is now adversarially generated. If I ran, there's no guarantee now anymore that the prover he maybe ran a different model to to generate the output. But when it commits to the trace, there's no guarantee that it's actually committing to the trace of this different model. It can commit to whatever he wants. And this means that our assumption about trace separation, meaning that the representational dissimilarity that came from using a different model, that's not really old anymore. In fact, there's a very trivial attack on the random node test, which is the adversary computes both M and M prime and commits to the trace of M except for the output. And now basically all the nodes will pass the test. But that's not necessarily true for the random path test, because that includes everything from the input to the output. So what can the adversary do? What the adversary can do is construct a fake trace that has a correct input and a bad output. And in this fake trace, so if the trace was the trace of the different model that created the output, we know that this trace is going to be very different. But if the trace is this adversarially constructed trace, if the adversary is able to compute a trace where many paths will evaluate correctly with respect to the weights of the correct model, then it's going to be able to fake us out. And so this is where we make this assumption that doing this is infeasible with overwhelming probability. At the beginning, we believed that this was infeasible, meaning that the probability to compute such a thing was negligible. And then we found out that this can be done, not with a much bigger, very big probability, but it can be done with a probability that is non-negligible. So why did we believe this assumption? The reason is that to construct this trace, it seems like a dual of the training problem, meaning in the training, you have input, output, and you keep changing the weights to minimize a certain loss function. Here, we're going to do the other way around. We need to keep the weights fixed because those are the weights that were committed in the ground truth, and the verifier is going to look at those weights. And we want to find a set of activation that minimize another loss function, which is the number of wrong paths. So we try this with two approaches. We try to break this assumption with two approaches, gradient descent and pseudo-inverse matrices, to try to figure out how easy it was to do this. And in our experiment, both approaches failed. So we started being very confident about this assumption. So turns out, and this was what we didn't know, but sort of came up during the reviewing of the paper, that there are other ways to build this fake trace, and there's something that has to do with the way AI models are backdoored. So you can sort of manipulate the weights of a model so that certain inputs will give you a particular output. And you can do the dual of that here. You can instead of modify a small number of weights, you can modify a small number of activations at a particular layer, and then keep the rest of the computation unchanged to produce a targeted output. So there is this particular attack that says, I want to produce Y prime. I'm going to run M up to a certain layer. Then at this layer, I'm going to flip a few activations, and then I'm going to continue on this modified value vector. I'm going to continue with the correct weights, and this will give me Y prime. So now our path test will still catch this, because at this layer L, there is this small number of nodes that have been changed. And if our path goes through one of those nodes, we'll see the difference. But if the path doesn't choose those nodes, then we don't. So that's why now our detection probability is going to be lower bounded by something like a constant. I have one here in the slides, but it's really a constant, the number of nodes that you have to flip over the layer of the network. So this could be not that small. So the adversary has a non-negligible probability of actually passing, but there is still also a non-negligible probability, a substantial probability of catching it. So an open question that this sort of raised was, there are ways to build models that are resistant to backdoor attacks. How can we, because this attack is a dual of the backdoor attacking, maybe the techniques that allow us to prevent backdoors may also allow us to prevent this kind of attack here. So we're looking at that. One thing that I want to sort of make clear is that even if the soundness is low, the soundness is still, a low soundness is still useful. And there are two reasons for that. The first one is that, and this is actually something that was pointed out to us at the beginning of this project when I was talking to somebody at Google. They were like, inferences are run so often and such large scale that even if you have low soundness, sooner or later, you're going to catch this party, right? So that's one reason. And the other one is that in certain application, you can put very high penalties on the on being caught cheating. And in that case, a rational party will not accept the risk of being highly penalized, even if the probability of being caught is not that high. Okay. So let me also say that we are using this notion of other model soundness. What do I mean by other model soundness? Which is the adversary is producing an output that comes from a different model. The adversary is not giving us an arbitrarily computed output. But the reality is that, first of all, those are most of the applications and the motivations in which an adversary wants to present a wrong answer is because he's trying to run a different model than the one that is supposed to running. But in any case, we are also able to extend our results to the case of an arbitrarily different output with once you have this sort of inherent upper bound of about 1 over n. Because if the output is different, there must be at least one internal value that is different. So this should be at least, this low soundness probability applies also to full soundness. So let me sort of close a little bit with some of our experiments. Here you'll see the difference between, on a 7 billion parameters, we went from almost 400 seconds to 6 milliseconds. Verification is also very, very fast. You see here that the proof size is much bigger, and that's because we're not using a typical snark. We're revealing all these parts of the network. So that's another trade-off that we pay for this much higher speeds. So let me tell you, and now I'm going to get, for the last 10 minutes, I'm going to get a little bit into some of the Cryptolets relevant parts of the stock. So one of the things that surprised me about these results was the following. This paper that we sort of compared ourselves with, the Zeki LLM paper from CCS 2 years ago, is based on this protocol called GKR, and some of you may know what that is. But one important thing about this protocol is that when you run a computation, in this case, your neural network, you don't have to commit to every single intermediate values like we do. That's one of the advantages of this paper. You don't need to commit to everything. But to run the GKR protocol, you need to take your computation and turn it into what is called an arithmetic circuit. So everything has to be turned into addition and multiplication, basically. And this introduced a very, very large overhead, especially in the arithmetization of the nonlinear activation functions. One thing that you might have noticed is that we're not doing any arithmetization. We're not turning our computation into an arithmetic circuit. We are using the circuit, the graph of the actual model. Everything we do is based on the actual native computation of the model. And on the other end, we have to commit to have all the intermediate values of this computation. So at the beginning, when we started working on this, my biggest question was, is the cost of committing going to kill us? And it turns out that also because we optimized the way we're using Merkle trees to get fast and shorter openings, is that committing an opening beats arithmetization. And that was something that I was pleasantly surprised by this work. So let me finish with a few open questions. Then I have another slide that I have in a different file that I'm going to put it up. So first question is, what we're using this notion of functional similarity, this relationship between functional similarity and representational similarity, there is no mathematical explanation for it. When I asked some of the AI people, I was like, well, it is obvious. We see it in the experiments, but no, there is no proof. There is no. And in fact, as a mathematician, what I would like to have is what's called an epsilon delta theorem, meaning something that connects the epsilon difference of the model as functions versus a delta difference between their internal representation. That would allow us to get more serious, more stringent, more grounded bounds in terms of soundness, probability, in terms of difference between our different are these models. So this is one big question. Another question is, are there other attacks, right? We missed one of the attacks that the reviewers told us, but are there more attacks on building this hybrid trace that is able to fool our path test? So, and this is how you get the best estimate for the soundness. And the first question is, can you do this in zero knowledge, right? This is a killer if you want to preserve the privacy of the model, because you reveal so many of the parameters during the computation. During the proof. One simple approach is to do composition. So run a protocol and then run a regular ZK proof on top of our protocol, where the prover knows proves in zero knowledge that he knows a valid proof for our protocol. The interesting thing is that now you're running the zero knowledge proof on a much smaller computation, which is just the verifier computation, not the original neural networks. It does involve a lot of hash computations because of the Merkle trees. You can do something like that. We actually, this is actually not true. We actually have done it, and we have some numbers that show that actually this is doable, but we have not really super optimized it or put it out there yet as code, but something that I would like people to sort of test. And there may be ways of doing something more ad hoc for this case. So to conclude, so let me conclude, but then let me put one more slide up. So we've been leveraging the statistical properties of neural networks. We achieve practical efficiency in terms of milliseconds, and we experimentally validated it. Again, there are these negative parts, which is what we trade for that, which is it's not zero knowledge. We don't guarantee exact correctness, and we have a somewhat low soundness in terms of our results. And so before I open this for questions, let me, hold on. Let me put one more slide. Let me see. This one. You guys see the other one? No?
Not yet.
Oh.
Okay.
You see it now?
Yep.
So this is the one that I wanted to put. I put it for this particular one. So, so how can we use hardware to speed things up here a little bit? So the first one is an obvious statement, right? Our proof uses Merkle trees. That's the only cryptographic part that we're using. So any ways to speed up hashing. What's interesting is this is actually where general snarks are going. It seems to be a pretty much the consensus that the production snarks are the type of snark that what are referred to also as starks, where the computation is encoded through error correcting codes and then committed through a Merkle tree. They seem to be outperforming the ones that are based on number theoretic assumptions or something like that. So again, any way to speed up hashing would actually work for general snarks, not just for our protocol. And actually, one thing that I was talking to one of my co-authors was that there's a lot of Reed-Solomon codes in this general snarks, and so that's also something where hardware support could help. Specifically for this protocol, as I said before, typical snarks for large models seem to be limited by the complexity of arithmetizing these nonlinear activation functions. And the question is it possible to have dedicated chips for the activation functions of LLM? Because maybe those not only will speed up, and this is coming from a theoretician, so this might be naive or not, but so this will actually, first of all, speed up the computation of the LLM itself, but maybe also provide what I call an hardware version of a lookup table. So a lookup table is this technique that has been used a lot into snarks to exactly deal with functions that are called several times inside a computation. So instead of in your big snark proving all these computations repeatedly, you build what's basically a verifiable lookup table that you say, what's the output for this function? And you get the output with a verification. And if you had a chip, you would have also like an hardware version of this lookup table. And so this would potentially speed up the computation of the proof as well. So those are two things that I wanted to throw out here as a non-hardware person that could sort of maybe be discussed. So, and this is really it. This is the end of the talk.
All right. Thank you, Rosario. Great talk. Thanks for that. We have a few minutes here. Does anyone want to ask a question?
So, I have a question, if you don't mind. Yeah.
Yeah, please.
Yeah. Thank you, Rosario, for the talk. My question is related to the performance. Mm-hmm. So it's in the other set of slides. I think you showed in your protocol the verification time takes longer than proving time. Is it just a statistical glitch because both times are in milliseconds, or there's a specific reason for that?
Did it take longer? Hold on. Let me go look.
I mean, not by a lot, but a little bit.
Yeah, okay. So let me see. You're right. It takes longer. Let me think. Oh, you know why? I'll tell you why. So remember what the verifier has to do. The verifier takes the values of the activations and the weights and checks that the perception equation works, right? That's the test of the verifier. When the verifier gets those values, he needs to verify them against the Merkle-tree. So the prover says, here are the activations and here are the weights that you requested with their Merkle-tree proof that they're correct, right? So the verifier needs to verify those Merkle-trees, and the weights Merkle-tree is the one that really, because if you think about, there's a lot more weights than there is activations. There is basically almost a quadratic. If you have n activations, there are about n square weights, right? Because those layers are almost complete. So the Merkle-tree of the weights is a lot bigger, and the verifier has to verify those weights opening on that Merkle-tree. The prover doesn't have to do any of that because the Merkle-tree for the prover was built once and for all at the beginning. So the prover just fetched those values and sends them out to the verifier. The verifier on the other end has to also verify the weights. I believe that's the reason why.
Okay, thank you.
I don't know if that answer makes sense. There's some sort of a symmetry between how many activations you have and how many weights you have.
I had a question on the proof size actually on this slide
Yeah.
too. So yeah, 1.7 megabytes. What do folks, in the industry trying to deploy these systems think about that, and how does that scale with the model size?
Oh God. So let's think about it. 7 billion parameters. So even if it's a byte each parameter, that's a lot bigger, right? So I always think it's you have to look about you're doing something that is about the square root of the size of the model. And the reason is that, again, if you think about at every layer, you're showing K values, where K is the fan-in of the model, right? Because you have to show all those weights and all those. And that is about square root. If you think that those layers are almost all full, that's about square root of the size of the model. So theoretically, that's what makes me happy, because it's quote unquote sublinear. In practice, this is not. It depends where your application is, right? This wouldn't fly, for example, on blockchain applications. While 183 kilobytes probably would. In other applications, maybe it'd be okay, but it's still on the large side.
Great, thank you. Does anyone else have any questions? All right. Well, thanks a lot, Rosario. And thank you everyone for joining us.
Thanks.
We'll see you all soon.
Sure. Thanks, everyone.